Oh, recording was not being done. No problems. We'll see that because recording is now being done. So if you don't mind, can I do it from start so that it will be easy for everyone who are not in the class not in the class today. So I'll repeat the process in a faster way. We have this ADL for doing Monte Carlo. We'll do ADXL, create new view. Okay. Then this, and then okay. There you reach this window. Now in this window, please see that you have the tests. This shows you the test available. You have simulator spectra, analysis, design variables, but you are doing it on the inverter. The name of your schematic and given in ADL. Then there are global variables. What is a global variable? You have in your ADL, please see your ADL very carefully. Whatever variables you have taken in your ADL becomes your global variables. You see, in the ADL, you have taken X as variable. This becomes your global variable, right? Now, because X is your global variable, you have taken it. I can take one more variable. For example, I take sigma. Right? Then there is what are the parameters you want to include? You don't want to include any parameter. What are the corners you want to include? I'll show you this part also. If you do not include any corner, it keeps on working on typical corners, right? We will do it on some process corner Monte Carlo also. Now, how Monte Carlo happens? From this window, you select the Monte Carlo sampling. These are the settings. Here you want to see, you want to do it for process or mismatch or both. I have selected both. What is the sampling method? It is random, right? Now, how many number of points you want to do? Given 200, you can use even 10,000 points for your simulation. Usually people take 2,000 to 10,000 points for their simulation. For your convenience, I'll take only 40 points so that I can show you like how it looks like. There is no need to save the process data. If you want to go with only database simulation, I repeat, if you want to go only with database simulation, suppose you want to calculate the power and delay, you calculate these two values, then there is no need to select anything except saving the process data. But if you want to, suppose we are working on these two wave shapes also, input and output. If you want to save any wave shape, then you have to select this, save data to allow family plots. If you do not select this, you will not be able to save any waveform, right? Now, how many number of points you have taken? 40. Select OK. Now you can start doing the simulation. Run simulation from here. You see what is showing, what is the minimum value, what is the maximum value, what is the mean value, what is the standard deviation. And here you see this simulation happening. This is a yield estimate of 100%. And it has passed 40 out of 40 points. I'll show you these all things. Please see. It has passed all 40 simulations, means all 40 simulations were correct. The minimum power is 8.981 nanowatt out of this 40 simulation. The maximum is 9.523. The mean is 9.23. Like standard deviation is 138.7 picowatts, means 0.138 nanowatt is the standard deviation. What is the standard deviation? Standard deviation is like when you deviate from the mean value. If this is a mean value, this is your standard deviation. How much you deviate from the mean value. And you see the delay minimum value is 30.88 picosecond. The maximum is 36.4 picoseconds. The mean is 33 and the standard deviation is 0.13. No, this is already in pico. This is 1.327 picoseconds. So these are your values, typical values. Now let us see how it looks like when you do such simulations. On doing such simulations, see this your Monte-Carlo simulation has gone 40 out of 40. This 40 out of 40 finished. Now you need to press this plot all waveforms. Shivansh says, I'm saying I got some message. Sir, it means less our standard deviation, more your more accurate. Yes, the standard deviation means from the mean value how much your results are deviating. I'll show you the deviation. You see, when I click on this, let me delete these values, clear all drawings. Now please see this window. I try to, no, it is not opening. I'll open it again. Okay. Please see this. This is your power. It is showing power over here. See, this is for power. The first plot. You see, it is starting from 8.8 and it is going to maximum value of 9.7. The mean comes somewhere here, which is 9.23. I hope you are getting what exactly this means, right? And there you see your delay results from this 29.4552 to 38.41 with the mean value of 33.436. That's how your plot looks like for 40 values. This is for your 40 values of power. Now, the most important thing I want to show you is this plot. Why I have taken the waves. Let us assume that I send it to or I move to a new window. Now see, these are the 40 output values, right? These are the 40 output values. Actually, let us see how these values looks like after simulations. You will feel the power of these simulations when you will see this wave shape. You see this. These are the 40 simulations. You see, these are the 40. I'll try to zoom it. See, these are the 40 different simulations. This is not just one wave shape. These are the 40 wave shapes together. This is a pulse which is going upwards this way. I was zooming this only pulse. This is actually the set of 40 pulses together. I'll zoom it again for you. There is only one pulse in this simulation. You see this. There is only one pulse. You can go for the down pulse also. See, this is going down. The set of 40 pulses together. Let us zoom it a bit more. I'm sure you might have got clarity that 40 simulations, how 40 simulations together look like. And if you see, assume that you are going to have 1000 simulations or 5000 simulation, how this wave will look like, right? This is the power of Monte Carlo simulation that you do. We can now I show you some other simulation so that you can get the more clarity on this. Now let me add one corner to it. It is already doing it on nominal corner. Nominal corner means it is using only one process corner, which is typical. Now I'll click here to add the corner. This window opens. This point will add another corner. You here click for model file. It selects the model file over here. Import from test. Okay. Now you select this C0. You can rename it to SF process corner, slow fast. And from here you can select your process corner. Apply. Okay. Now you see here in window, you have two process corners. One is nominal, which is typical, and the other is slow fast. Again, you see Monte Carlo simulations. You have 40 points and you press OK and you go for simulations again. Now you see this Monte Carlo simulation happening. You see now it is showing that 80 simulations are taking place. Can you see this? Is it visible to you that the 80 simulations are taking place? Now, if you see this, there you get the power, which is typical corner. There you have power in slow fast corner. Delay in typical corner, delay in slow fast corner. In this corners, you see the minimum delay in typical corner is 8.981. In slow fast is 9.028. The average is, the maximum is 9.52, 9.59. The average is 9.23, 9.28. The standard deviation here is 138 pico, and here you have 143 pico. Let us come to the delay. There you also see more distinction. The minimum delay is 30 in typical, 35 in slow fast corner. Means the delay is higher in slow fast corner, the minimum delay. Similarly, maximum delay is also higher. 41, here you have 36. There you have average delay 33. There you have 38.09. The deviation is 1.32 and 1.34. Deviation is almost very close. Now there is a term in Monte Carlo simulation which is called variability. What is the variability? Variability is standard deviation divided by the mean value. So you have standard deviation of 1.343 divided by, for this Stovers corner, 35.49. And for this typical corner, you have 1.327 divided by 30.88. That will give you the value of variability. Which process corner is more variable? Now, what we'll do, we'll see the plots. See, these are the plots. This is the power for your typical corner. This power is for slow fast corner. This delay is for typical corner. This delay is for slow fast corner. And if I remove this, yes, there you have V in and V out for, let us do one thing, take it to the new window. What it is showing? It is showing the 40 points for nominal and 40 points for slow fast. Means there are 80 simulations are there now. Let us see how these simulations look like. See, these are the 80 simulations for typical corner and for slow fast corner. These are the 80 simulations. Similarly, you can move this to here. The pulse falling down, output falling down, the output rising up, the output rising down. You can see there directly that if you see this falling down wave, the variability is less. This variability is very less. The pulses are very close to each other. And if you see this going up, the variability is way higher. The pulses are distinct. So variability is actually visible with the naked eye also, but you need to find the specific values of the variabilities for your research analysis purpose, right? So that's how we do Monte Carlo simulations, and that is how the. If see one more thing I want to tell you, if you wish to see all the values, you have done it for 40 corners for this slow fast, 40 corners for this typical. You want to see all values. You can see that. You can go to details. It will show you all the values. See what is the nominal value, what is the minimum value, what is the maximum value, what is the value for slow fast corner. It gives you all the values in this table. For every random input, you will get the output values. You can see all the 40 values. Right? So this, in particular, Monte Carlo simulations in the Cadence Virtuoso is a very effective tool that can give you every type of analysis which is available in this VLSI circuit design. In the circuit designing in specific, you require all these variations, all these values, so that you can 100% get affirmed that my simulation or my values are correct in every sense and my device is workable. Right? Now, please ask me if you have any questions. If not, then I'll move to the other topic for the day. Although I have tried from my end to cover each and every bit of it, but still, if you have any doubt, you can ask.
Sir, can you explain typical values एक बार फिर से मतलब कि
Typical
typical
values.
values मतलब होता कैसा है उसमें typical value मतलब सर जैसे कि आपने कहा ना कि हम typical values ले रहे हैं तो typical value मतलब है क्या जैसे slow fast तो सर समझ में आ गया पर
हाँ,
typical value
देखो ऐसे ऐसे समझो शिवांश,
random value
ऐसे ऐसे समझो, जैसे स्लो का मतलब है यू आर टेकिंग हाई वीटीएच, फास्ट का मतलब है यू आर टेकिंग लो वीटीएच, और टिपिकल का मतलब है विच आर द स्टैंडर्ड वैल्यूज. You have three type of MOSFETs. One is high VTH, one is low VTH, one is standard. So high VTH you can take as slow NMOS. Low VTH you can take as fast NMOS, and standard VTH you can take the typical values. Typical values वो values हैं जब आप normally simulation करते हो जो value आती है. That is called the typical value. जब आप नॉर्मली पहली बार में सर्किट रन करते हो जो आपका केडेंस आपको जो वैल्यूज दे रहा होता है, दीज आर एक्चुअली द टिपिकल वैल्यूज. दिस इज कॉल्ड टिपिकल कॉर्नर. इसको आप स्टैंडर्ड कॉर्नर कह लो, टिपिकल कॉर्नर कह लो, नॉमिनल वैल्यू कह लो, नॉर्मल कॉर्नर कह लो, कैसे भी कह लो. बट आपका डिवाइस, आपका एनमॉस और पीमॉस नॉर्मल स्टेट में जब रन हो रहा है, जब उस पर कोई इंपैक्ट नहीं है, कोई स्लो फास्ट नहीं है, कोई टेम्परेचर नहीं है, तो हम उस वैल्यू को कहते हैं दीज आर द टिपिकल वैल्यूज ऑफ एनमॉस एंड पीमॉस इन द सर्किट.
ओके सर एंड सर आपने क्या कहते हैं एक मोंटे कार्लो सिमुलेशंस में एक सिग्मा वैल्यू भी ली थी।
हाँ।
तो वो तो सर क्या कहते हैं, वैसे तो हमने एक्स वेरिएबल ले रखा, तो वो सिग्मा वैल्यू डिफाइन क्या कर रहा है?
जब आप
सिग्मा की
लोग
वैल्यू आपने अपनी ली थी।
जब आप लोग स्टैटिस्टिक्स पढ़ोगे ना, तो उसके अंदर सिग्मा की वैल्यू डिफाइन होती है। आपने शायद वो प्लॉट्स को ध्यान से नहीं देखा। वो जो प्लॉट है वो भी सिग्मा की वैल्यू ले रहा था। You want to know what is the meaning of what when I said sigma is equals to 3
यस सर, वो मतलब डिफाइन क्या कर रहा है सिग्मा इक्वल्स टू 3?
in statistical simulation?
हाँ जी सर।
मुझे उसके लिए एक बार फिर से उस पर जाना पड़ेगा। मैं एक बार उस पर जाता हूँ वापस। Somehow my computer got hanged. Sorry for that, but now it is working. अरे ये तो नई तरह से करना पड़ेगा। You just see that I'm doing this process because my ADL values somehow not got saved, but no worries, I can do it in 2 minutes. Okay, given the value, now go to ADL. Okay, and ADL. Okay, Shivansh, I think this plot is visible to you.
यस सर।
This power plot. In this plot,
यस।
the meaning of sigma means uh, the value of sigma. See, this is -3 sigma. This is +3 sigma. पता नहीं ये वैल्यूज मेरे पास ना स्केच नहीं दे रहे मुझे अभी। इफ आई कैन शो दिस, ये -3 सिग्मा है और ये +3 सिग्मा है। 3 sigma is a value in statistical design where shows which helps you to create a plot that is neither too far from mean value or not too close to mean value. That is why we take sigma is equal to 3. There are the three, suppose, let me give you one example. If I have, suppose, I have the mean as a 50. Let us assume that I have a mean as a 50. And in 50, I take sigma is equals to 1. If I have mean is equals to 50 and I take sigma is equals to 1. So sigma is equals to 1 means that 68% of the values will fall between 47 and 53. When sigma is equals to 2, sigma is equals to 2 means the 95% values will fall between 44 and 56. And when sigma is equals to 3, it means 99% values will fall between 41 and 50. Right? So this sigma actually gives you the difference between the minimum value and maximum value. And it tells you that how many values will exist between minimum and maximum. When we use sigma is equals to 3, the statistical measure shows that your range will be wider. See, there you have range of only 6 points. Now the range is wider. The range is of 10 points. But in this wide range, 99% values exist. That is why I take the value of sigma is equal to 3. It is not specified anywhere because I read this statistical simulations and statistics part. If you read the statistics as a subject, then you see that how these value of sigma work. Sigma is equals to 3 is a particular value in the statistical simulation which will give you a particular range. जैसे इसके अंदर what range you have 8.5792 to 9.82. Probably if you use sigma is equals to 1, this range will get narrower, but the less values will exist between this range. So this sigma is equals to 3 give you higher range, but 99% of your statistical values will exist between this range. Now, why I'm talking about 99% values? We are doing just 30 simulations in this case. Just assume the case if we are doing 10,000 simulations. Then you want a certain values, maximum and minimum. In between those values, all the values should exist. अब मैं आपको इसका एक और एग्जांपल देता हूं so that you can understand it more clearly. Let us assume कि मेरे पास ये जो मिनिमम वैल्यू और मैक्सिमम वैल्यू है ना, ये मिनिमम वैल्यू ये मेरे पास ना 10,000 पॉइंटर सिमुलेशन है, राइट? आप ये अज्यूम करके चलो 10,000, ये जो सिमुलेशन है ये 10,000 पॉइंट का सिमुलेशन. अब इसमें जो आपके पास मिनिमम वैल्यू है ना, वो आ रही है आपके पास 8.8 की जगह 2.8 नैनो, और जो मैक्सिमम वैल्यू है वो आ रही है 20.6 नैनो, और जो मीन वैल्यू है वो 9.2 के पास ही है. अब देखो 9.2 से 2.8 कितना दूर है और 20.6 कितना दूर है. अब क्या होता है, वो क्या करेगा जब ये वाली वैल्यूज लेगा ना, इन दो वैल्यूज को आपके प्लॉट जब बनाएगा, उस प्लॉट की मिनिमम और मैक्सिमम में से जब वो इसका मीन डिसाइड कर रहा होगा, तो उसमें से यहाँ जो 2.8 वाली वैल्यू ना, बहुत दूर वाली, इसको एज्यूम ही नहीं करेगा. इस 20 पॉइंट वाली को एज्यूम ही नहीं करेगा. वो सिर्फ 99% वो वैल्यूज एज्यूम करेगा जिन वैल्यूज का कुछ इस प्लॉट के अंदर जो मैटर करती हैं. जो वैल्यूज बहुत कम या बहुत ज्यादा है और इस प्लॉट में मैटर नहीं करती, वो उनको निकाल देगा. दैट इज व्हाई वी टेक इस सिग्मा इक्वल्स टू 3, जो आपके प्लॉट की मैक्सिमम वैल्यूज भी एज्यूम कर ले और आपको जो मीन वैल्यू है वो ठीक दे दे. दैट इज व्हाई आई टेक सिग्मा इज इक्वल्स टू 3. इफ यू टेक सिग्मा इज इक्वल्स टू 2 तो या सिग्मा इज इक्वल्स टू 1, तो आपका वो प्लॉट ना ऐसा बनाएगा. ऐसा हो सकता है आपको मीन वैल्यू सही दे दे, बट इन प्लॉट आपको बहुत सारी वैल्यूज बाहर छूट जाएंगी. और अगर आप सिग्मा इक्वल टू 4 लोगे तो सारी वैल्यूज एज्यूम कर लेगा शुरू से लेके एंड तक, बट वो जो आपकी मीन वैल्यू वो गलत आएगी. राइट? दैट इज द सिग्निफिकेंस ऑफ यूजिंग सिग्मा.
Okay, sir.
I hope.
And sir, अगर हम 10,000 सिमुलेशन भी कर रहे हैं तो वो तो सर सिमुलेशन में बहुत टाइम लगेगा ऐसे।
हाँ, it takes time. It takes time. Even a single simulation in Monte Carlo takes sometimes more than 1 hour, 30 minutes, 40 minutes. It depends on the speed of your system, speed of your computer, that how much time this simulation will take,
थैंक यू सर।
right? सो मुझे लगता है कि हमारा आज बहुत सारा टाइम फिर से इसी के अंदर कंज्यूम हो गया कि वी हैव कंज्यूम्ड अ लॉट ऑफ टाइम इन ऑल दिस पार्ट ऑफ Monte Carlo simulation and process corner simulation, although this simulation was also very important. But the point is, like, I wanted to start with the memory today, and we are left with only 5 minutes in this meeting. If you all say, then I can start with this simulation. If you are all agree, I can start with the memory part. Shall we start? It will take at least half of the other third meeting also. If you all agree to it, I can start. Okay. Ajay, the PhD scholars are always agreed to do all these things. Let us see the other people, what they are. See, if you are all agree, then
Yes.
we can start. Should we start with the memory? Okay.
Yes, sir.
Let us start and let us do the basics of the memory, and we'll elaborate the part tomorrow. Right? I'll tell you the basics, the very basics of the memory. Simulations इसका कल सिखा देंगे. Okay, so SRAM. Initially, we'll talk about only 60 SRAM cell, 6 transistor SRAM cell. What the SRAM cell is all about? SRAM cell is 1 bit storage of data. And in this case, its storing element is inverter. How do we save the data in the memory? We have this inverter, and to this inverter we have attached one more inverter. Now this is called latch. If you somehow be able to produce 1 over here, you will get a 0 over here, and this 0 will go as an input to this, and this inverter will make 1 of it. I hope this is very simple thing I have told you, that if somehow you produce 1 over here, this inverter will make 0 from 1, and this 0 will travel to the input to other inverter, and this inverter will make the 0 to 1. So that is how the basic storage element works. Now the point is how SRAM is different. SRAM, random access memory, is able to read the data, write the data, and because it is a memory, it is able to store the data. We will see all these 3 parts of the memory, that how the memory reads the data, how the memory writes the data, what is the meaning of storing the data. What process you have seen here is called storing the data. This given a value and the value get fixed in a latch is a storing the data. And once you have the data inside the latch, it has a value 0 on this side, it has the value 1 on this side. Reading these values externally, because when you give a command, your memory give you access to the data, and you start reading that whether it is 0 or 1. When you get access to these values, this process is called read. You will read 1 over here, you will read 0 over here. And changing this data from the external influence, somehow you make this 1 to 0, you convert this 1 to 0, and then this 0 will automatically get converted into 1. this will become 1, and this will become 0. Changing the data of this memory externally, this is called write. Right? So there are three things I've told you, that this latch can store the data, you can read the stored data, and when you try to change the stored data, that process is called the write process. Right? Now this class is going to finish in a few seconds. Let us join on the same link again, and I will explain you the circuit diagram and how the read-write process actually happens inside the RAM. Right? So let us close this meeting and we'll join on the same link again, so that I can tell you. This is a very important part and very interesting also. And this is used in most of the industries.